1. The Sun's Disdain. The Birth of Icarus's Dream, Ancient Crete. The human fascination with flight is more than a mere technical ambition. It is an epic narrative that begins in the crucible of mythology, driven by a profound, primal yearning for freedom. Against the brilliant, shimmering backdrop of the Aegean Sea, near the high, unyielding cliffs of Crete, lies the scene of our oldest, most cautionary tale. For countless millennia, the sight of gulls tracing perfect arcs across the sky had been a silent, elegant mockery of our earthbound condition, an ache of envy that demanded action, a constant reminder of the vertical dimension we could not conquer. We look upon the figure of Daedalus, the archetypal inventor and grieving father. His face, etched with the deep lines of both genius and profound fear for his son's safety, is framed by long, silver hair whipping frantically in the unnatural wind he has created. He flies ahead, his movements desperate, yet precisely controlled, propelling his body with wings meticulously crafted from hundreds of bird feathers, carefully layered and held together by beeswax and fine linen thread. His frantic, desperate warnings to his son are torn from his lips and scattered by the turbulence and the sheer, overwhelming vastness of the sea below, already far too small. But his son, Icarus, embodies the reckless, intoxicating spirit of pure, unchecked aspiration. He is a youth of almost blinding beauty, his dark hair unbound and catching the sun, his strong, youthful body carried aloft by his borrowed instruments. He does not see the technical risk that concerns the mechanic. He sees only the limitlessness of the blue expanse, the sheer, exhilarating joy of defying gravity and the limitations set by man and God alike. The realm of the gods, to him, is not a sacred boundary, but an open, irresistible invitation to glory and freedom, an escape from the labyrinth of the human condition. The climax arrives with an almost visceral certainty, the moment ambition overtakes engineering. The air carries the sickly sweet scent of melting wax, and a dark, telltale tear of bee glue tracks down Icarus's arm. He looks up, his youthful features contorted in a terrifying mix of awe and dawning panic, as the brilliant golden sun so close, so magnificent begins the ultimate consumption of his mechanism. The feathers, his only anchor to the air, detach not in a single mass, but in tiny individual spirals, tragically bright against the dark sea below. Icarus plummets, a momentary tragic star extinguished. The sea that closes over him is forever marked by his impossible ambition. The myth of Icarus is not a simple tale of failure, but a complex paradox, the caution that fundamentally fuels the dream. Man's first attempt at genuine flight was a magnificent imaginative feat, a necessary instruction set for failure, and the first blueprint for the technological future. 2. The slow ascent, from gliders to practical power, Europe and America. The centuries following the myth were marked by isolated, often tragic, empirical attempts. We see the historical records detailing figures like the 11th century English monk, Aylmer of Malmesbury, who, convinced he could fly, leaped from an abbey tower with rudimentary wooden wings. These accounts confirm a recurring theme: human muscle power was utterly inadequate for sustained flight. The Renaissance, however, brought a necessary shift to scientific rigor. Leonardo da Vinci meticulously filled his notebooks with sketches that were not fantasy, but rather the first true scientific blueprints for aerodynamics, detailing ornithopters and early parachute designs based on the anatomical study of birds, applying rational mechanics to the problem of flight. His theoretical work anticipated much of later engineering, though the necessary power source was still centuries away. The crucial turning point came with the Industrial Revolution and the advent of two technologies. First, the powerful internal combustion engine, offering an unprecedented power-to-weight ratio, finally solving the power deficit. Second, the systematic, dangerous experimental work of German engineer Otto Lilienthal. Lilienthal, a robust, bearded figure often photographed mid-leap from engineered hillsides, rigorously tested the principles of lift and control with oversection and eusection. 2,000 successful glider flights. He generated the first reliable aerodynamic tables on wing camber and lift coefficients before his fatal crash in 1896, leaving a legacy of crucial, empirical data for those who followed, effectively sacrificing his life for the principles of stability. His work directly influenced the final breakthrough in America, where a different, more meticulous focus on control was key. The scene shifts to the remote, wind-swept outer banks of North Carolina, specifically Kill Devil Hills, on a cold morning in December 1903. The light is gray, the air sharp. The final mechanism is ready. The Wright Flyer, constructed of spruce wood, cotton fabric, and a struggling four-cylinder engine designed and built by the brothers themselves, a masterpiece of lightweight engineering that weighed barely 700 pounds. Two brothers stand ready, Wilbur and Orville Wright, quiet, methodical men from Dayton, Ohio. They were bicycle mechanics, approaching the problem not as physicists, but as engineers focused on the subtle art of balance and three-axis control, pioneering the critical concept of wing warping. Orville, focused and mustached, takes the controls, lying prone on the lower wing for better weight distribution. The engine sputters, catches with a violent rattling sound, and the machine shudders down its launch rail. At 10:35 a.m., with only 4 witnesses, the impossible occurs. A moment of acceleration, a stagger, a lurch, and then an unmistakable rise. The flight lasts only 12 seconds, covering a mere 120 feet, a distance shorter than the wingspan of a modern jumbo jet, but a fundamental chasm in human capability had been crossed. Man had achieved sustained, controlled, heavier-than-air flight. The era of imagination gave way decisively to the era of the machine and empirical science. 3. The golden age of aviation and global bridging. The Wrights' success ignited a furious global competition, turning their humble design into an international pursuit. Across Europe, innovators raced to perfect the design and prove its utility. Louis Blériot, a French inventor who wore thick spectacles and a determined expression, captured global attention in 1909 by being the first to fly across the English Channel, an audacious 37-minute journey that proved the airplane was more than a localized curiosity. It was a revolutionary vehicle for connecting continents and defying natural barriers. The airplane was immediately pressed into devastating service during the First World War, accelerating development at an unthinkable pace. Fragile wooden biplanes were quickly supplanted by metal-framed fighters, transforming pilots into the new, celebrated knights engaging in dramatic dogfights in the skies above the trenches of Europe. This brutal testing ground rapidly advanced engine power, maneuverability, and structural integrity, leading to the development of crucial wartime technologies like synchronized machine guns and reliable air-to-ground radio communication. The aircraft evolved from a flimsy scout to a decisive weapon in under 4 years. The 1,920 seconds and 30 seconds ushered in the golden age of aviation, an era defined by endurance, spectacle, and celebrity. Charles Lindbergh, a lean, quiet Midwesterner with an aura of stoic determination, became the ultimate global hero in 1927, completing the first solo, non-stop flight across the Atlantic in the spirit of street. Louis, navigating by dead reckoning alone. This act transformed aviation into an industry of mass ambition and heroism, opening the door for commercial transatlantic travel. Similarly, Amelia Earhart, with her iconic determined smile, goggles, and purposeful gaze, broke gender barriers and countless speed and altitude records, becoming the global face of aviation adventure before her final mysterious disappearance over the Pacific, a stark reminder of the frontier's persistent dangers and the thin margin between success and catastrophe. These long-distance flights, often carried out by organized national formations, such as the massive transatlantic cruises led by Italy's Italo Balbo in the early 1932, cemented aviation's role in global answers, commerce, and national prestige. Commercial aviation began its slow ascent with luxurious flying boats, like the famous Pan Am Clippers and early airliners, beginning the process of shrinking the world and making the dream of air travel a widespread, eventual reality accessible to the global middle class. 4. The jet age, the sonic threshold, and high-altitude frontiers. The Second World War delivered the next quantum leap, the jet engine. Simultaneously pioneered in Germany, Hans von Oheim, and Great Britain, Frank Whittle. The gas turbine offered a revolutionary thrust that immediately rendered the propeller obsolete for high-speed flight. The power of chemical propulsion reached a new level, transforming aviation physics from lift and drag to the complexities of shockwaves and compression. The post-war focus was entirely on speed, leading to the frantic, competitive era of the Cold War. In the barren high desert of California, at Muroc Army Airfield, the U.S. Air Force was determined to break the theoretical speed limit. The vehicle was the rocket-powered Bell X-1, a machine shaped like a stub-winged orange bullet, designed to withstand the immense pressure of the speed of sound. In October 1947, Captain Chuck Yeager, a slight, unflappable man, flew the X-1. The speed climbed toward Mach 1, the speed of sound, a physical barrier many feared would disintegrate any aircraft. At 43,000 feet, the sonic boom announced the victory, a ground-shaking shockwave that confirmed man had mastered the atmosphere's natural speed limit. The decades that followed saw the full realization of the jet age. Commercial airliners, exemplified by the streamlined Boeing 707 and the revolutionary wide-body 747, made mass air travel possible, transforming global demographics and economics. Simultaneously, military aviation pushed performance to its absolute limit, challenging not just speed but altitude. The Lockheed SR-71 Blackbird, a sleek, menacing black reconnaissance jet that looked unlike any other aircraft, could fly routinely at Mach 3, 2, and at altitudes exceeding 85,000 feet. The pilots, flying in pressure suits, were essentially astronauts in the upper reaches of the atmosphere, constantly flirting with the limits of human physiology and the atmospheric ceiling. The F-104 Starfighter, a highly maneuverable interceptor, was often flown to heights that technically qualified its pilots as true astronauts, blurring the crucial line between air and space. 5. Modern air dominance, hypersonics, stealth, and swarms. Today, the modern fighter jet is the ultimate expression of human control over the vertical frontier. The current apex predator is the fifth-generation stealth fighter, like the Lockheed Martin F-22 Raptor or the F-35 Lightning II. These machines are dark, angular diamonds, an aesthetic defined by low observable technology. Their bodies are precisely designed to scatter and absorb radar waves. Their skin is a composite tapestry of sensors and electronic warfare systems. The aircraft is a fully integrated flying supercomputer, capable of fusing data from multiple sources across the battlespace and acting as a stealthy node in a larger network. The pilot, nestled in a streamlined cockpit featuring advanced helmet-mounted displays, acts as a command hub. The high-pitched, continuous whine of the powerful turbofan engines is the sound of hyper-tuned technological muscle, delivering immediate, breathtaking vertical thrust and supercruise capability sustained supersonic flight without the use of afterburners. The new horizon for air dominance is hypersonic flight speeds exceeding Mach 5. The development of experimental aircraft like the X-43A and X-51 Waverider is proving the viability of the scramjet engine, which uses the aircraft's forward motion to compress incoming air for combustion. This technology promises to deliver missiles and surveillance platforms to any point on Earth within an hour. This extreme speed challenges material science itself, requiring new alloys and cooling systems to withstand the immense heat generated by air friction and sustained high-speed operation. However, the definitive future is defined by cognitive warfare and autonomous integration. The Next Generation Air Dominance (NGAD) program is not a single aircraft, but a system of systems centered on a sixth-generation penetrating counter-air (PCA) fighter. Crucially, it is designed to fly as the commander of a massive distributed network. Alongside it are the Collaborative Combat Aircraft, CCA, uncrewed, highly autonomous, AI-powered loyal wingmen. These drones, often referred to as remote carriers, are expendable, adaptive, and operate under the pilot's command in a secure, instantaneous network known as the Combat Cloud. The human pilot transitions from the traditional hero of the stick and rudder to the fleet commander of a sophisticated, autonomous swarm. The drive of Icarus, to command the air, has culminated in technological mastery. But the final, most profound leap lay beyond the atmospheric ceiling, the age of the rocket. 6. The rocket's dawn, the race to the ultimate altitude. The pursuit of true cosmic travel began not with lift, but with thrust, the powerful, controlled explosion of the rocket engine. The theoretical work of pioneers like Russia's Konstantin Tsiolkovsky, who first articulated the mathematics of rocketry, and America's Robert Goddard, who launched the first liquid-fueled rocket, laid the foundation. But the practical, high-power liquid-fueled rocket was realized by German engineers, primarily Wernher von Braun. His efforts led to the creation of the V-2 missile, which demonstrated the terrifying power and ultimate potential of a technology that could breach the atmosphere, unburdened by wings or air friction. After the Second World War, the technology and the key personnel, including von Braun, were divided, fueling the tense geopolitical struggle known as the space race. The scene is the vast, cold, open landscape of the Kazakh Soviet Socialist Republic. In October 1957, the Soviet Union launched the R-7 Semyorka, turning a weapon into a ladder. Sergei Korolev, the brilliant but often anonymous chief designer, watched as the massive rocket, topped by the simple metal sphere of Sputnik, climbed toward the darkness. The mighty earth-shaking thunder of the engines gave way to the distant, regular BEE, PBEE, PBEEP of Sputnik, in orbit, the ultimate announcement that man now had a footprint in the solar system, ushering in the age of satellites and instant global communication. The race to put a human into orbit was short, dangerous, and intense. In April 1961, Yuri Gagarin, a Soviet cosmonaut with a famously warm, youthful face, was strapped into the cramped Vostok 1 capsule. His ecstatic cry, "Poyakali, let's go," marked the moment he completed a single orbit, becoming the first person to witness the Earth as a magnificent, lonely blue jewel from space. He famously described the planet's atmosphere as a thin, fragile film of protection, fundamentally changing humanity's perspective on its own vulnerability. This victory spurred the American response, the Apollo program. Led by President Kennedy's audacious goal, the program involved over 400,000 engineers, scientists, and technicians working with unprecedented focus. The iconic imagery of mission control, with engineers in white shirts and narrow ties, tracking every detail, culminated on the dusty, desolate surface of the Moon in July 1969. Neil Armstrong, the stoic commander, delivered the unforgettable words as he stepped onto the lunar surface. The dream of Icarus was not just realized, it was transcended. A new trajectory had been set. Human movement throughout the solar system was now possible. 7. Permanent presence and the commercialization of orbit. The decades following the moon landing saw a shift in focus from mere exploration to the establishment of a permanent, sustainable presence in low Earth orbit, LEO. The International Space Station, ISS, a massive, gleaming habitat and scientific laboratory the size of a football field, became the ultimate symbol of global cooperation in the cosmos, requiring modular construction and continuous resupply from multiple nations. The continuous hum of its life support systems and the vast flow of data proved that human life could be sustained indefinitely outside the planetary atmosphere, offering a unique microgravity research environment. The early 21st century marked a radical shift with the rise of commercial spaceflight. Private ventures, led by visionary innovators like Elon Musk and his company, SpaceX, and Jeff Bezos with Blue Origin, revolutionized access to space. The development of fully reusable launch vehicles, such as the Falcon 9 and Falcon Heavy rockets, drastically reduced the cost of accessing LEO and made routine orbital delivery possible. This commercialization transformed the aerospace industry, shifting the power dynamic from government agencies to private entrepreneurs driven by efficiency and the vision of extraterrestrial colonization. This new era is defined by the Artemis program, which aims not just to revisit the moon, but to establish permanent infrastructure there. The immediate goal is the Lunar Gateway, a compact, powerful space station being constructed in a unique, elliptical orbit around the moon. This station will serve as a vital staging post, a necessary bridge between Earth and the Moon's surface, where astronauts can reside and prepare for lunar excursions. The continuous development of massive, reusable mega-rockets NASA's SLS and the private Starship are the key technological drivers, transforming rockets from disposable transports into genuine, repeatable ferry services. The ultimate objective is clear: to establish a continuous, self-sufficient base near the Moon's south pole where water ice is concentrated, called Artemis Base Camp. The Moon is transforming from a destination to a proving ground, a resource hub, and a necessary cosmic gas station for deep space travel. 8. The Martian Staging Post and Planetary Engineering. The ultimate human objective remains the red planet, Mars. The plan for Mars is predicated on the concept of sustainable independence, focusing heavily on in situ resource utilization, ISRU, using local, Martian resources to live and travel. The scene is the near-future interior of a pressurized habitat on the surface of Mars. The light is reddish, illuminating the complex, critical network of life support systems, hydroponic farms, and machinery designed to process the alien environment. Outside, the vast, cold, orange-red desert stretches to the horizon, dotted with massive domed structures and the early traces of human infrastructure. The atmospheric pressure is barely 1% of Earth's, yet it will be transformed. An astronaut engineer, perhaps Dr. Sharma, is visible through a dusty porthole, performing crucial tasks in her Mars suit. Her job is not merely discovery, but manufacturing and planetary engineering. She is using the planet's own dust, or regolith, and its concentrated water ice to create rocket fuel, methane and oxygen, breathable air, and 3D printed building materials for shelters. The MOXIE experiment on the Perseverance rover already proved the concept of converting atmospheric carbon dioxide into oxygen. This is the cornerstone of the entire strategy. Mars is not the final stop. It is the ultimate staging post, a cosmic fuel depot and shipyard for the journey to the outer solar system. The focus shifts beyond survival to terraforming the long, multi-century process of potentially modifying the Martian environment to make it more Earth-like by releasing trapped gases and initiating global warming. This ambition, the engineering of an entire world, represents the ultimate application of the knowledge gained from Icarus's failure, demonstrating humanity's capacity to not just survive, but to profoundly adapt to new environments. This move towards self-sufficiency represents the complete triumph of knowledge over mythological fatalism. The Icarus paradox is fully resolved. We must fly into the sun's domain, but we must do so armed with knowledge, redundancy, and engineering to temper the wax of ambition. 9. The Starlight Fleet. Interstellar Dreams. What happens after the solar system is colonized? Extrapolation suggests a relentless, accelerating outward spiral of human presence driven by curiosity and the necessity of redundancy. The limits of chemical propulsion are already giving way to next-generation drives. Current concepts explored by cutting-edge labs and programs like NASA's Innovative Advanced Concepts, NIAC, are challenging physics itself. Pulsed fusion propulsion, which uses massive, controlled atomic blasts to propel a ship, and advanced ion drives and solar sails that leverage the sun's energy and magnetic fields to achieve incredible velocities over time. The concept of nuclear thermal propulsion offers a massive efficiency increase necessary for faster interplanetary transfers, finally shrinking the months-long journeys to mere weeks. The scene shifts dramatically to deep space, hundreds of years from now. A massive, complex starship, the Daedalus Ascendant, occupies the frame, or a world unto itself, an O'Neill cylinder, or an arc powered by controlled fusion, or perhaps even the highly efficient, massive energy release of matter-antimatter annihilation. This cylinder does not fly, it sails or accelerates through the light years, a self-contained civilization in a bottle, traversing unimaginable distances across the galactic void. The internal ecosystem is self-sustaining, a biological world carried through the darkness. The goal is interstellar flight, a slow-motion epic journey measured in generations, with the crew navigating to exoplanets' worlds orbiting distant suns across the Orion arm of the Milky Way. The The ship's captain, her face bearing the subtle, genetically engineered marks of generations born in low or altered gravity, stands at a holographic interface. Her eyes are distant, reflecting the starlight of an entirely new, far-off stellar system, the ultimate frontier of human endeavor, the final fulfillment of the dream sparked on a Cretan cliff millennia ago.